Okay, so in first part we will continue with electronic switches, and then we will move to millimeter wave link budget and noise calculation, and in presence of noise how we characterize any millimeter wave system. So let us continue with electronic switches. So last day we are discussing about a given switch, we can use it in shunt configuration as well as in series configuration. Now usually looking at the value typical capacitance or resistance values, a few ohm or capacitance a few picofarad, that we have seen that in shunt configuration the switch will give better isolation. Now let us say whatever isolation we are obtaining from any given switch, it is not enough. So in that case how we can improve the isolation further? So in that case we can use the same switch two numbers in series shunt configuration. So here is one example. So you can see one antenna, it is connected to receiver side and transmitter side. So now when the transmitter is connected to antenna, in that case the switch whatever we are using in series configuration, it is in on condition, and in shunt configuration it is in off condition. So that means in equivalent circuit in right hand side shown here. So in on condition the switch will replace by its equivalent resistance R series, and in off condition will replace its by equivalent capacitance which is C off, and in this situation we call it a series shunt configuration. Similarly right hand side can be modeled. Right hand side together these two switches it forms a series shunt switch, and it is in off condition. So the switch or a pin diode which is off we represent it by C off, and the switch which is in on condition we represent it by series resistance which is grounded. So now how isolation improves in this case? So we see, let us consider the switch which is in off condition, that is the receiver side. So this pin diode, the first one, it is open circuited, so it is represented by a capacitor. So capacitor will give you some isolation. Further the second pin diode, it is switched on. So if there is any RF signal, it will be further grounded. So we have actually isolation improvement from the contribution of these two switches. But looking at the insertion loss value, it won't be that good. If I consider now left hand side for the transmitter side, so in that case isolation insertion loss will increase because of the resistance and the capacitor, because in addition to the resistor we have a capacitor which is also grounding some part of the RF signal. So insertion loss it will be poor. But anyway, for any given application the main point is the difference between the insertion loss and isolation, how we can improve this difference. Now let us see plot of figure of merit versus frequency. So left side it shows insertion loss, and right hand side it shows isolation versus frequency for different figure of merits. Now for the insertion loss plot, what we expect, that instead of single switch, if we use series shunt configuration, insertion loss will be higher. So let us compare 200 femtosecond. For this one at 140 gigahertz insertion loss is almost 6 dB. Now if I compare this one with previous case, let us go back to previous one. So here with R on equal to 4 ohm, you can see insertion loss at 140 gigahertz it is 3.5 dB approximately. So in series shunt configuration insertion loss increases. Now look at the isolation values. For 200 femtosecond at 140 gigahertz we have at least 15 dB isolation. But if I go back in the previous case, in this case for 200 femtosecond you see isolation is less than 5 dB at 140 gigahertz. So using series shunt configuration this isolation has been improved from 5 dB to at least 15 dB, and the same logic is true for other figure of merit values. So, what is the conclusion then? We can use series shunt configuration to improve isolation at the cost of little increased insertion loss. Now, some cases we may face problem due to input impedance matching problem. Why? If I go back to this circuit, one switch we are using in series configuration, another one in shunt configuration. So, as a whole this switch is on. So, now whatever impedance seen by the antenna, if I change the state of the switch when it will be off, that means this resistor is open and the capacitor and this off, this series resistance we have to replace by a capacitor, and this shunt capacitor we have to replace by a resistor. In that case, the input impedance seen by the antenna, transmitting side, everything will change. And not only that, in series or shunt whatever we consider, so the capacitance or resistance whatever given by the switch, it depends on that particular device. We do not have any control over that. Now, for a 50 ohm system, we should match the input impedance. So, sometimes may happen if we simply buy some switches and use in the circuit. So, input impedance matching it may be very poor. In that case, how we can improve the impedance matching? We can use some inductors simply to improve the impedance matching. So, let me show you an example. So, in this particular isolation and loss plots for a SPDT switch with matching inductor. So, when we add matching inductor, we add a small value of inductor in series with the switch, and the value of inductance L series, it can be given as Z0 square multiplied by C series plus C shunt. So, C series corresponds to the capacitance of the switch in off condition, whatever we are using in series combination connection. Similarly, C shunt, this is the capacitor of that pin diode which we are using in shunt configuration. So, then the matching inductance value, it depends on these capacitance values and the system impedance Z0. Now, if I look at the source of losses when the switch is on, so we have mainly losses because of the resistance. So, resistance, it is defined by fabrication process, and for resistance improvement it can be done by changing the W by L. So, where W represents the width of any MOS gate and L represents the length. Same true for pin diode, it W in that case it represents the cross section, L represents the length. So, by fabrication process then we can tune the resistance values. Now, look at this plot. So, insertion loss it increases, but return loss it has a minimum value and it is a function of figure of merit. So, for a given inductor then and for a given capacitance value, we have some optimum value of R for which return loss will be minimum. So, for this particular example, when we are using R series equal to 4 ohm, R shunt equal to 7.2 ohm at 60 gigahertz, in that case we are having minimum return loss approximately at 130 to 140 femtosecond. Already we have discussed how to implement a switch by using PIN diode. Now, let us see how we can implement switch by using FET. Now, in FET or NMOS or PMOS, both are available in market, but usually when we go for high frequency applications, NFET or NMOS is preferred. Why? Simply because electron mobility is higher than the hole mobility. So, we can use NFET at even millimeter wave frequencies, and there are some alternatives also. Already we know the devices. For example, we can use also MESFET as a switch, we can also use HEMT as a switch, but in all the cases we will prefer electrons as the carriers. So, in general we can represent a FET MOSFET by this. So, we have this is a 3 terminal device. If we neglect the body terminal, then we have source, drain and gate. The control voltage is applied at the gate terminal. Now, if I look at the variation of drain current versus VDS, so this first part of this graph, it looks like a straight line. We call it the linear region or the triode region, and after that for a given gate to source voltage, if we keep on increasing the drain to source voltage, then this current components it's become constant, or we call this is the saturation mode of the FET. Now, when we use it in switching application, in that case we will be using this linear region and the cutoff region of the FET. So, linear region it occurs for VDS, this is less than VGS minus VTH, where VTH this is the threshold voltage and VGS is the gate to source voltage. Then in that case drain current, drain to source current, this is mu n into C dielectric into W by L, this ratio multiplied by VGS minus VTH into VDS minus VDS square by 2 ampere, where the C dielectric it represents the gate capacitance. It depends on the whatever insulation we have used for the gate and the thickness of that insulation. So, C dielectric it becomes a process parameter. Not only that, W by L it also a process parameter which depends on the fabrication procedure, and here L is the channel length and W is the width of the gate. So, the on state resistance we can consider a VDS value sufficiently smaller, then in that case R on that is equal to L by mu n C dielectric into W into VGS minus VTH ohm, and the channel is off, the switch is off, then when VGS is less than VTH we do not have any inversion layer inside FET. So, if LOV is overlap length between the gate and the source or drain, so off state capacitance we can represent like twice epsilon dielectric into W L overlap divided by T dielectric, it is in farad. So, for this given FET, then we can calculate what is the figure of merit. It comes simply R into C, which is twice L LOV divided by mu n into VGS minus VTH, and the unit is second. Now, for improved figure of merit, what we have to do? We have to decrease the channel length. Similarly, we have to decrease the VTH. So, W by L it is a process parameter. In that case, we have to use the minimum value, so that you can have the less figure of merit value for improved performance of the switch. So, how we can decrease VTH? We can increase the dielectric constant of the insulator whatever we used, and the thickness of the insulator that should be also as small as possible. Another way, we can use some group 3 group 5 material inside which carrier mobility is very high. For example, gallium arsenide, indium phosphide or gallium nitride. So, if the carrier mobility is higher, in that case we can expect that R on will be much smaller. Some heterojunction structure like gallium arsenide, aluminum gallium arsenide, they also exhibits high carrier mobility. Stress engineering also increases carrier mobility. So, the stress engineering last day I was discussing that another crystal let us say germanium or maybe silicon. So, one crystal it is just if we place this crystal on another one and if we use a very thin layer, in that case the first crystal it will try to follow the second crystal, and sometimes the effective carrier mobility, it depends on the crystal structure. So, we can force the second layer to follow the first layer's property. So, this is called the stress engineering. Now, in CMOS technology, usually the figure of merit is very high, and that is why it is not popular at millimeter wave frequency. So, typically they are used below 30 gigahertz. So, here is one example of IL, RL and isolation plot for a CMOS NFET designed using 65 nanometer technology. Typical R series value is given as 5 ohm, C of 36 femtofarad, and T technology, its figure of merit, it is coming 182 femtosecond. Sometimes we can use parallel inductors to improve the performance of the switch. So, this FET itself, it will give you some capacitor, and inductors together it forms a resonating circuit, and it behaves like a band pass filter. So, that is how sometimes we can improve the performance of a FET switch. So, here is one example of NFET switch with inductors. So, for this typical switch, we are using 520 picohenry in series and 3.5 nanohenry in parallel combination, and that will give a band pass filter like response. The response is shown here. So, you can see insertion loss, it is minimum at the resonating frequency approximately 41 gigahertz. Not only that, due to that resonance behavior at this frequency, return loss is maximum. So, we have very less reflection from the input of the switch, and also isolation is maximum. Now, one problem with FET or CMOS switch is that whenever we are using them, we are considering only small signal equivalent circuit and switching between the cutoff state and linear region. But let us say one FET switch already it is in cutoff region, we are expecting that switch will be in off condition, but the applied electromagnetic signal magnitude is so high, sometimes it can turn on the FET. So, we can't use it for very high power applications. So, this is a limitation for FET switches. So, there is an alternative that we can use stacked FET configuration. So, here is one example, stacked FET device. So, instead of one, we are using 3 FETs in parallel shunt configuration. So, whatever voltage we are applying, it is now being divided into 3 components. So, that is how we can improve linearity of the given FET switch, but only one problem is that conventional CMOS fabrication procedure, they can't fabricate this type of stacked FET. So, we have to use some non-standard procedure and fabrication cost will increase. Another important point, when we go for high power applications, so what is the 1 dB compression point of the switch? So, you remember that we are assuming the switch as a linear device. So, here how we obtain that 1 dB compression point, this is first we have to plot the output power versus input power. It should follow a straight line if it is a linear device, but for high power it starts to deviate from the straight line, and when this deviation is 1 dB, the corresponding input power we call the 1 dB compression point of the switch. Here this is a plot for a typical FET switch, and we see for this particular switch 1 dB compression point is at 40 gigahertz, and it is coming for 3.6 dBm of input power. So, here is performance comparisons. we have different type of FET switches in HEMT technology, in travelling wave HEMT technology. So, what is travelling wave HEMT technology? Here multiple HEMT switches, they are used in cascade connections by using a by separation of transmission line section. So, we use some transmission line among the FET switches to connect them, and that is why we call it travelling wave type HEMT. So, if we compare these switches performance, we see the insertion loss is lower for reference 3 and the blue one reference 4. So, mainly the HEMT and PHEMT switches, they are better performance compared to conventional FET switches. Look at the isolation values. Again, PHEMT switches, they are providing at least let us say 30 dB isolation over 60 to 70 gigahertz. Typically, switches using standard 90 nanometer or 130 nanometer CMOS technology, we used below 30 gigahertz because of their very high figure of merit values. Now, we know different technologies. We have FET switches, HEMT switches, PIN diode switches. So, let us compare their performances. So, these are the major performance comparison of some switches which are available commercially in market. So, measured values for FET switches typically at 77 gigahertz, it is providing insertion loss 2.7 dB, isolation 29 dB, and we see figure of merit is 264 femtosecond. For gallium arsenide HEMT at 60 gigahertz, we see figure of merit is 324 femtosecond, but for PIN diode it is just 30 femtosecond. So, PIN diode among these three is better performer. Here are some more examples. In almost all the cases, we see that PIN diode it is providing lower insertion loss as well as better isolation. Now, what are the challenges associated with electronic switches? So, the first example is maximum power handling capability. P max, it can be given by E g to the power 4 into V s square by F square, where E g this is the band gap energy. So, higher is the band gap energy, maximum power handling capability is higher. V s is the saturation velocity. If the saturation velocity increases, in that case also we can increase power handling capability, and it decreases with increasing frequency. So, different materials will provide then different maximum power handling capability. Now, if we use PIN diode, although in previous chart we have seen that PIN diode it is providing minimum insertion loss and maximum isolation even at 100 gigahertz and beyond, but the main problem with PIN diode is the biasing current. For PIN diode, typical bias current it can be as high as 10 milliampere or even more than that. Now, consider we are using a phased array antenna or similar type of applications where we have hundreds of switches. So, it will consume very high DC power. So, it is a problem for PIN diode. Next, for FET, the problem is its lower power handling capability. For high power applications, we can't use FET switches, but the advantage of FET switch is its low power consumption compared to other switches. Similarly, gallium nitride or gallium arsenide switches, although they provide better figure of merit compared to FET switches, but we face integration problem, high contact resistance. So, finally, we have to provide some contact switch by using some sort of metals. Then third order intermodulation, so it can generate high frequency components. Then high negative pinch up voltage, typically for gallium nitride based switches. So, here are some examples of fabricated switches. These are some photographs. Left hand side shows millimeter wave CMOS switches. So, this top layer, this spiral, they are actually inductors. So, we can't fabricate inductor inside chip, we have to fabricate the inductors on top of the chip. So, you can see this spiral, they represents the inductor. So, not only inductors, we need also capacitor. So, inductors and capacitors they use for RF and DC blocking. Right hand side pictures, it shows several pin diodes with their packages. So, they are based in rectangular waveguide technology. Inside the rectangular waveguide, pin diode is housed. You can see for a given component, this small aperture, it shows the input line, we have output line on the other side, and the SMA connectors, they are actually using for the biasing or the control signal. These are some name of the companies, different types of switches available from these companies. So, we will take a break, then we will start millimeter wave propagation.